Okay, this week we're going to talk about the planetary circulation. So we're bringing all these variables that you've learned about together now to discuss how air moves around the whole planet and why that occurs. So, what are some of these principal features that contribute to this planetary circulation, and how do they affect the weather where we live or other areas? Well, let's see if we can look at the broad picture. So, if we had a non-rotating Earth, life would be so much easier. Of course, we wouldn't be able to live here, but life would still be easier. Uh, we would have two areas. One where the dark side, things would fall and sink over here where it's cool. The other where the sunlight hits, convection would cause them to rise. So you would have basically two circulations. But we have a rotating Earth. Doesn't work that way. So what that creates is belts of winds. So between 30 degrees north and 60 degrees north, where we all live, winds are generally westerly. If you go south of that, less than 30 degrees north, they're generally from the east. And if you go to the North Pole, tight circle, but they generally tend to be from the east, and then on the other side of the globe, they come from the west. So winds blow with and against the planet's rotation all over the place here. What that generates is, if you looked at that pattern, you get low pressure around 60 degrees north and high pressure around 30 degrees north, predominantly, most of the time. Southern north, over the North Pole, there's extreme low pressure at the upper atmospheres there, but we're talking about the surface here. And here's what it actually looks like during January. Low pressure right around 60 degrees north, several of them here. High pressure, 30 degrees or a little bit below 30 degrees. And the whole pattern shifts with the sun. So where it was a little further to the south in the wintertime, it's going to be a little further to the north in the summertime. This big high that sits over the Atlantic, sometimes called the Bermuda High, but it is what causes the Gulf Stream, that gyre that's there for the Gulf Stream to live. So with that, you have these subtropical anticyclones, and where you have an anticyclone, remember, air is clear, the air sinks, so that's what it does right along 30 degrees north. So actually, if you were wanting to sail a boat and you were at 30 degrees north and you just had wind, you would not get a lot of motion because it's basically the doldrums there. You've got to go a little bit south of that or a little bit north of that to get more winds. Poleward, we have the westerlies, which is where we live, basically. And then there's two subpolar lows, the Aleutian low and the Icelandic low. And in the southern hemisphere, more continuous belt of low pressure surrounds Antarctica. And there are fronts that ride down through this belt. With these lows moving to cross to our north, they push fronts down and push high pressures behind them. That's why the westerlies have so much change in weather. We're not all bad, like maybe further north may have more and more low pressures. We're not all great, like down towards the tropics where it's sunny most of the time. We have the transition zone. And then there's the polar vortex. Every year, more and more articles are coming about the Atlantic oscillation, the Arctic oscillation, which is what the polar vortex is. Basically, you keep getting colder and colder in one area. We know the air sinks. You're going to get a very tight, very cold rotation in that area. And the stronger that air rotates around the pole, the less chance it has of slipping out and coming south to make our area very cold. But when it does break down, that's when we get our Arctic outbreaks down in the United States. In the mid-latitudes, you can see here we have these westerlies with a trough and ridge. And with that, the tropopause oscillates in the mid-latitudes. Down in the Arctic, it's pretty low because it's cold and dense. Down in the tropic, it's pretty high because that's where it's warm, humid. And in between, tropopause can go up and down, and we're going to look at that later. So the south of that big old high pressure, you have trade winds that are in the Atlantic coming across from the east. And this is a descending branch, and you wind up getting uh, pretty stable underneath that sometimes. And over Hawaii, they're kind of in that area. And they wind up not getting as many thunderstorms and all because they have a trade wind inversion in that area. Another interesting thing is the intertropical convergence zone, which is basically the area where the southern hemisphere winds converge into the northern hemisphere winds. That moves. Think about it. Ocean water does not change a lot in temperature. It has requires a tremendous amount of heating to warm it. So it doesn't move a whole lot. But the land, on the other hand, notice that the intertropical convergence zone is well south of India during the wintertime, and well north of India and parts of Thailand and all during the summertime. It has a major impact on the weather in those areas. It creates monsoons. So once it moves north of that area, you wind up with southeast winds into India, southerly winds into the Indonesia and all that, and wind up with a lot of rain, very wet summer pattern. However, in the wintertime, it's moved south. So what you wind up with is winds coming out of Siberia where there's no moisture, a very dry pattern. So there's two distinct wet and dry seasons where monsoons like this occur. And guess what? We have one in the United States too. There are other features of these systems. On the eastern edge of one of these big ocean high pressure systems, the air is sinking. And it's also coming from the north. So it has a dry component. And you can see, like in San Diego here, during the summertime, hey, don't get rain. More in the wintertime when the high shifts a little bit to the south, allowing some storms maybe to come in. However, Charleston, South Carolina, which would be on the west side, is more unstable. Lots of moisture being brought up from the tropics, so they get the heavier rain in the summertime, but they get rain all seasons long there. These semi-permanent features actually contribute to the ocean currents. When we talk about the Gulf Stream coming out of the Gulf of Mexico and up along the eastern coast of the United States, when you think about it, there's high pressure. North Atlantic high pressure right here. What's it doing? It's pushing that warm air north. That's why England actually stays a little bit warmer than it would otherwise be. Here is the monsoon for the United States. We actually have one. What happens is you heat up. There are some higher plateaus out here in Mexico that get very hot in the summertime. So that causes a low pressure, because the air is less dense right there, to form at the surface. And because the low pressure formed there, that begins to bring moisture in from both the Gulf of Mexico and from the Pacific, converging into that area. Above the low pressure at the surface is actually high pressure. And that keeps this moisture flowing right around that area so that they get almost all their rain in the southern part of Arizona and New Mexico comes from this monsoon circulation. Rossby waves. They're basically long waves in the atmosphere. We'll talk a little bit more about those in a little bit here. Here you can see two kind of flow patterns where we live. One is more zonal. It does have a little wave pattern to it, allowing weaker fronts, and they move very quickly. One is more meridional, moves much further south, much stronger lows, and much stronger cold or warm air coming in with them. And then you get blocks in this pattern. What happens? We've had one that's been sitting up off the New England coast for a while. Messed my week up by keeping the air coming off the ocean more, keeping me more clouds. But these blocks tend to stay, basically they lose track of the jet streams up here, and they just kind of get separated from it. And you get ridges and troughs, and the flow just doesn't go through them. Eventually they do break and then begin to move again, and the flow changes to a more zonal pattern or even a meridional pattern. But they can hold weather in over an area for a long, long time, sometimes weeks. And these patterns like this have been known to produce flooding in the Midwest. They have been known to produce extremely cold air coming off the Great Lakes into the eastern United States. It just depends on where they set up. And that is one of the criteria each year that you're looking at, where they're going to set up. And here you can see long waves in the westerlies, blocking systems. all that rainfall in the Midwest. All right, when you go up and there's a trough in the atmosphere where low pressure is to the west and high pressure is to the east, across that, remember there's a sloping 250 millibar or a sloping 300 millibar surface there. So what you created is a tight pressure gradient. And if there's a stronger and stronger temperature difference, that pressure gradient is even going to get more impressive. And that's why the jet stream forms, because some of the strongest temperature gradients are up in the upper part of the troposphere. Coriolis effect, we know, balances the horizontal, create the gradient wind, and these jet streaks sometimes develop with winds over 200 miles per hour every once in a while. If you ever hear about a jet that makes it from California to the East Coast in record time, many times that's aided because of the jet streak. And you can see the seasonal shift. During the summertime, the main jet streak is further north. Wintertime is moving all the way down the southern part of the United States. And along this, there are ridges and troughs, and where they are, winds may slow down or converge, and there'll be high pressure that actually forms at the surface under this wind for convergence. Where they speed up, more divergence, and you wind up with low pressure. So this is a real fast way to say, oh, I may have a 500 millipattern like this, but at the surface I have high pressure and low pressure. They don't correspond to where the highs and lows are along. And you can see that with looking at the divergence and convergence with this whole pattern here. And here is the jet streaks, where you see this maximum wind. The left front quadrant up here is where a lot of divergence occurs, in the right rear quadrant. So there's the areas of divergence and convergences in the other areas. There are other tropical or global patterns that are associated, and these can actually be related to both ocean and the atmosphere. They're El Nino and La Nina. They have a major impact, especially on the western United States, but they have some impacts even further east. Currently, we are heading and trending towards a La Nina. So these are the oscillations. You can see how they vary from year to year. Another thing that goes on in the oceans, and this I have observed at times off of Cape Hatteras and off the Outer Banks. If the wind is from the southwest, think about it, the air, you're pushing the ocean current towards the northeast, like it would be with the Gulf Stream. Well, remember, if you have a wind blowing to the northeast, it wants to turn to the right because of the Coriolis. Well, the same happens in the ocean. So what happens is you actually spin with time more and more the ocean currents away from the coast. Well, if the ocean is moving away from the coast, the ocean's got to keep the coast still have water. Where does it come from? From the bottom. So when it does that, it really can cool off very dramatically along the Hatteras, the Outer Banks. Some days it could be in the 80s, and one next day it could be in the 50s. So with El Nino and the warm phase, you get air pressure falls over the eastern Pacific and rises over the western. The pressure gradient weakens, the trade winds are not as strong, and they may actually reverse. So here you can actually see lots of convection out here in the thermocline moving down, which is where the La Nina is just the opposite. Usually caused by a lot of upwelling in the eastern tropical Pacific, which is what is going on right now. And all of a sudden, all that convection and stuff is now way west and not so far east. And it changes up the flow pattern tremendously. There's another North Atlantic oscillation, which is the seesaw variation. There's a positive and a negative index. Here you can see the positive index, high pressure, stronger, low pressure up here. Here you have more stronger high pressure, low pressure. It depends. All it is a relationship between this high over the Atlantic and low over Iceland. And that impacts the eastern part of the United States immensely. Here's the Arctic Oscillation, which I've told you about as an indicator of when Arctic air may move into the United States. The stronger the AO is, the less chance it's going to move in because the circulation is so tight. When it begins to weaken, there's a better chance for Arctic air to come plunging down. So positive phase, lower pressure over the poles, stronger winds there. Negative phase, more cold winters. And here you can see the difference on those. There's a Pacific decadal oscillation as well, where the warm phase, lower SSTs, above average along the coast of Alaska, and well-developed dilution lows. And then we have the Madden-Julian Oscillation, MJO. This is an area of convection that develops typically in the Indian Ocean and slowly migrates to the east. The stronger the convection is, it can enhance the rainfall phase, and it actually was more evident when high SSTs are there. And with that enhanced rainfall phase, you can actually bring more moisture into the Pacific Northwest or parts of the United States. And this will move across over the whole globe with time and then reoccur. It has a great influence on the Pineapple Express or atmospheric rivers in the United States. So with that, I just wanted to show you a couple things real quick. This is the current jet stream. So if you look at this, here is one jet stream. Here is a Rossby wave, a long wave in this part of the atmosphere here. High pressure kind of building up here, so it's a ridge. Here's another Rossby wave. This one's kind of too close, so it's going to tend to want to move over more. But right now, though, this pattern is blocked. Here is this block that's been sitting here, keeping us from getting there. We got another good Rossby wave here. And when you look at some of this, you can see the equatorial temperature anomalies here. Notice how much colder now with depth. That's what's cooling parts of the area aloft. And here you can see with time, it's beginning to be reflected with cooler temperatures in parts of it. And here you can actually see where the warm water is. Now this is a pattern that's moving towards a La Nina. Here you can actually see some of the anomalies. And here's Nino 3.4 typically is where they look, and you can see the trending down almost to 3/4 of a degree now, cooler than normal. So that would be where you would expect to say, oh, there may be some beginning towards La Nina. And the Climate Prediction Center also looks at these large scales anomalies like the Arctic Oscillation. Right now it's very positive. So holding the cold air north. The North Atlantic Oscillation had been negative, but it's beginning to trend back upwards. So this is just some of the stuff used to look at the global weather pattern. So I hope you got something out of all that, and if you have any questions, please don't hesitate to ask.